This lesson is on bounds. In the first half of the lesson, I'm going to explain the basics of rounding and finding bounds and why we do this process. And in the second half of the lesson, I'm going to explain some typical exam questions and show you how you should approach them. As always, if you want to navigate to the right part of the video, the links are in the video description. Okay, rounding and bounds. What are they and why do we do them? Let's start with rounding first, as it should be more familiar to everyone. Why do we conduct the rounding of values? Well, it's quite simple. We don't care sometimes about the accuracy of some measurements that we take. When we're measuring the space for a new sofa, we don't care about that measurement to the nearest millimeter. We probably only care about it to the nearest centimetre or maybe even 5 centimetres. And when we're cooking, we don't need to know the weight of sugar that we have to add to our cake to the nearest milligram. It would be fine just to know this value to the nearest gram. So how do we conduct rounding? Well, you should be pretty familiar with this already, but let's go over a couple of quick examples. You're going to be given a value and told to round it to either a number of significant figures or a number of decimal points. The first significant figure is the first non-zero number in your value, and the second and third and fourth significant figures continue on from there, from the left. When you're rounding to a number of significant figures or to a number of decimal places, you need to look to the number after that level of accuracy. So if I want to round to 2 decimal places, I look at the third decimal place. Or if I want to round to 2 significant figures, I look at the third significant figure. When I look at this figure, the figure that comes afterwards, I look to see whether or not it's 5 or greater or less than 5. If it's 5 or greater, I round the value before it up, and if it's less than 5, I'm going to round the number before it down. Here's a couple of quick examples. If I was rounding to the nearest whole number, 42.3 would round down to 42. 42.4 would also round down to 42, but 42.5 would round up to 43. If I was rounding to 3 decimal places, 0.1592 would round down to 0.159, but 0.1595 would round up to 0.160. Because it was 59 and I've rounded the 9 up, I need to move the 5 up to 6 and it becomes 60. Okay then, so what are bounds? At this stage I'm going to bring in a page from the RedTick textbook to demonstrate what bounds are. So on the left we have a situation which we might go through if we were rounding figures. Let's say you went to the doctor's surgery and had your height measured. And your height was measured to a high level of accuracy, say 0.1 of a centimetre. If you then had to quote your height to people, you might not want to round it to the nearest 0.1 of a centimetre, so you might round this value to the nearest centimetre. This is rounding and that's it, basically. Now let's look at what the opposite is. Let's say you are a very good sports star and you're going to a training camp. And at this training camp they're testing your athletic ability. They're doing a jump test, and for the jump test they need to know your height so that they can work out how much spring you've got in your step. And you fill in your height to the nearest centimetre. This is put into a computer, and the computer requires the height to a higher level of accuracy. The computer needs to know it to the nearest 0.1 of a centimetre. The computer might have an algorithm then that would compute the upper and lower bounds of the value that you've put in. If a height of 175 centimetres was input into the machine, the algorithm would compute an upper bound of 175.5 centimetres and a lower bound of 174.5 centimetres. These are the biggest and smallest values that the exact value could have actually been. And the computer might then use this to work out a max and minimum level of springiness in your step. So how do we find upper and lower bounds? Well, there's two ways to think about this. Let's talk about the proper way to think about it first. When you're asked for the upper bound of a value, you will be told what the value you've been given has been rounded to. And what you're really been asking is, what is the actual exact value of this figure could be? Let me give you an example. If I recorded the length of my commute to work to be 5 miles to the nearest mile, it would be the case that the upper bound of this value would be 5.5 miles. And the lower bound of this value would be 4.5 miles. The lower bound's a little bit easier to understand. 4.5 miles is the smallest value which would be rounded up to 5 when rounding is conducted to the nearest mile. As soon as it drops below 4.5, 4.4 anything, that value would have been rounded down to 4 miles and not rounded up to 5 miles. Now looking at the upper bound of 5.5 miles, ask again the question, what is the biggest value that would have been rounded down to 5 miles instead of being rounded up to 6 miles? Well, the truth is that it would be 5.49999 recurring miles. But because this is essentially equal to 5.5 miles, we say that 5.5 miles is the upper bound of 5 miles to the nearest mile. Here's some more examples. If you were given 220 to the nearest 10, the upper bound would be 225 and the lower bound would be 215. If you were given 107 to the nearest whole number, the upper bound would be 107.5 and the lower bound would be 106.5. And if you were given 1.66 to the nearest 2 decimal places, the upper bound would be 1.665 and the lower bound would be 1.655. As you can see with all of these examples, the level of accuracy that I've been given the original values to determines where I place the 5s in my answer. If I've been given a value to 2 decimal places, in the 3rd decimal place I place a 5. And if I've been given a value to 2 significant figures, the 3rd significant figure is where I place my 5. This is a very easy way to get half of finding upper and lower bounds right, but you have to be very careful when finding the lower bound. If I'm finding the upper bound of 2.5 to the nearest 1 decimal place, I can simply add a 5 on in the 2nd decimal place to get 2.55. But to find the lower bound of 2.5 to the nearest 1 decimal place, I have to drop down below 2.5 and change the 5 to a 4 and add the 5 on in the 2nd decimal place to get 2.45. This complexity means that asking yourself the question, what is the smallest value which would round to the value I've been given? Or what is the biggest value that would round down to the value I've been given? This is the really good way to compute the lower bound and the upper bound respectively. Now I'm going to explain 2 of the typical exam questions that we get on upper and lower bounds. The first one is what I call the garden fence problem. Picture you're at a friend's house and one of the adults in the friend's house tells your friend to go out with a measuring tape and measure the length of the garden fence. Say whoever asked them to do it wants to go and buy some new fencing. Your friend goes out, they come back in and they say it's 12 meters. The adult might then ask them, is that to the nearest meter? And they would say yes. And then you might be brought in to find out what is the upper bound and lower bound of this value. Now, why does anyone care? Well, if you're going to the shop to buy fencing, you don't want to buy too little. And if your friend only measured to the nearest meter, what is the actual largest amount of fencing that might be needed when the adult goes to the shop? Let's draw a diagram to see how this might work. Imagine a garden fence out the back of a house which has fencing on 3 sides of the garden. The 2 sides of the garden are 12 meters long and the back of the garden is 5 meters wide. And let's say there's a gate in one of the sides which is 1 meter wide. If all of these figures are to the nearest metre, and we want to know what the maximum amount of fencing that might be needed for the garden are, we need to work out the upper bounds for each side of the garden to compute the maximum amount of fencing needed. The upper bounds of the back of the garden is 5.5 metres, and the upper bound of the side of the garden is 12.5 metres. But then we have the gate. Well, the gate measured 1 metre. We have to consider what actual value of the width of the gate would maximise the amount of fencing that we needed. So we assume that the gate is as small as possible. We take its lower bound of 0.5 metres. We would then subtract this from the overall width of that side, which was 12.5 metres, to give us the maximum amount of fencing that might be needed for that side of the garden. We now have 3 figures that we need to add together: 5.5, 12.5 and 12. This is the maximum amount of fencing that would be needed for this garden. The second type of question is what I call the bounds formula question. You're going to be given some sort of formula in terms of letters, and you're going to be given values for each of those letters to a certain degree of accuracy. If we were given the formula capital A equals x minus y over z and told to maximize the value of A, we need to consider the top and bottom of the fraction in the formula. Consider this. If I told you that you could pick any 2 digits between 1 and 9, including 1 and 9, and I was going to divide one digit by the other and give you that amount of money, you would really like to pick 9 to go on the top and 1 to go on the bottom, as that gives you £9. As soon as you start reducing the number on the top, the number of pounds I give you goes down, and as soon as you start increasing the number on the bottom, the number of pounds I give you also goes down, to the point where you put a 1 on the top and a 9 on the bottom, and you get about 11p from me. What this demonstrates is, when we want to maximise a fraction, we maximise the top line and minimise the bottom line. The smaller the thing you're dividing by, the bigger the answer. So in this question, we want to maximise x minus y, and we want to minimise z. Well, how do we maximise x minus y? Well, that's a bit easier. We maximise x minus y by getting the biggest possible value of x and the smallest possible value of y. Once we've gone through this process, we know that we're trying to find the upper bound of x, the lower bound of y, and the lower bound of z. In this example, with x equal to 5, y equal to 2, and z equal to 3, this leaves us with 5.5 minus 1.5 divided by 2.5, which is 4 divided by 2.5, which gives us 1.6 as our answer. Every time you face one of these questions, consider the top and bottom of the formula that you've been given, and ask yourself, what would maximise the value of the entire formula? It might be the case that you have to minimise the value of the entire formula, where the top of the fraction has to be as small as possible and the bottom of the fraction has to be as big as possible. You can then move on from there and find out whether or not you need to find the upper bound or the lower bound of each of your values.